The next expiration policy is idle time based. And in this policy, data is considered or the cached entry is considered valid as long as it is being accessed. In this approach, an entry is considered stale if it has been idle for a specified duration of time. So same as time-based expiration, in this approach also we use a timer, a TTL property. The only difference is in this case or in this policy, the timer is reset every time when the cache entry is accessed. And that is done to monitor the idle time. So let's say we have a cache entry and that cache entry is not being accessed. In that case, the TTL or the time will not be reset. That means ultimately the timer or the TTL property will expire. And when it happens, the entry will be considered as stale or outdated. As an example, this approach can be used in user sessions. So user sessions are active as long as user is active. And when the user is idle, not active for a long period of time, then we can mark that session as stale and outdated, and that session can be expired. So idle time-based expiration is suitable for use cases where the cache data is directly tied to some kind of client activity or user interaction, and the cache data is not relevant when not actively accessed for a specified duration of time. And this kind of policy optimizes this space by expiring the entries that have been idle for too long. We'll see a sample implementation of idle time-based expiration to understand how it works. It's only a pseudo implementation, not a complete implementation. So here we have an entry class that represents a cache entry, and same as time-based expiration, we have the data, the last access time when this entry was last accessed. And we also have a TTL for idle time threshold. So whenever we create a new entry, we pass the data. We set the last access time, which is the current time when this entry was created. And we also set the idle time threshold. This is same as TTL. So this entry has the information when it was last accessed by using this variable last access time. And if we check the sample code of the cache, so in this case, whenever we return the entry from the cache, first of all, we check if the TTL or the last access time has breached the idle time threshold. So by using the current time and the last access time of that entry, we can check if the idle time threshold has been breached. And if it is the case, we can refresh the entry. And whenever we do the refresh, we set the data from the source and we override the last access time to the current time. All right. So it invalidates the idle time in a sense. But let's say if the threshold has not been breached, it means the entry is still valid. So before we return the cached entry, we update the last access time. And in this way, this kind of implementation tracks the idle time of the entry. And the entries would be marked as stale or outdated based on this access time. Now in this policy, it's important to choose an appropriate idle time threshold or the TTL. And to do that, we need to consider the expected frequency of data access so that we can strike a balance between the liveness or the freshness of data and the performance that we require from the cache. And it may not be a preferable solution for the use cases where the cached data is continuously accessed and very frequently, because in that case, most of the items will never breach the idle time threshold. So that means the items will always remain active and they would not be expired. So we may need to choose the threshold accordingly. We may need to choose the use case appropriately in order to use this kind of policy. So in short, idle time-based expiration provides a way to optimize the caching by refreshing the entries only when they have been idle for a specified duration.